The first paper will be register tiling for unstructured sparsity in neural network inference. Our speaker will be Lucas Wilkinson. Wilkinson. Lucas performed this research while he was a master's student at the University of Toronto. He now works on accelerating compressed neural networks at NeuralMagic, a local company. This paper presents an innovative technique designed to improve hardware utilization for sparse programs. The author illustrates how this method boosts performance by creating specialized code that maximizes register reuse, customized to fit the sparsity pattern. Looking ahead, we believe this approach holds broad applicability beyond SpMM on CPU, potentially accelerating various sparse applications in the future. Lucas, please share your screen and go ahead.
Okay, cool. Thanks for the introduction. You guys can see my screen, right? Okay, cool. Awesome. So, as mentioned, I'm Lucas Wilkinson, and this was work done in collaboration with my co-first author, Kazem Cheshmi, under the supervision of Miriam Denavi. So there's no secret that neural networks are everywhere these days. And with that comes like a desire to make them both smaller and faster and more computationally efficient. And one technique for doing this is pruning. And the basic idea of pruning is that after the network's trained, not all of the weights are equally as important to the performance of the network from an accuracy perspective. So you can actually remove a bunch of these connections and still maintain the accuracy of the network. And there's been a lot of advancements in pruning recently, and so we can prune a lot of modern networks with minimal accuracy loss. And so this is great in theory because it can both theoretically reduce the model size on disk and in RAM, and also theoretically reduce the compute requirements. However, in practice, realizing these speedups is actually very challenging because the network that's left is highly unstructured in nature, and getting that to map onto modern hardware, which really likes structured computation patterns, is challenging. So just to step back a little bit, the way neural network inference works is that we typically lower these down to highly optimized linear algebra routines. So here, for example, if we have a small dense MLP network where we have a vector of activations going through this network, it gets multiplied by a static weight matrix and resulting in a new vector of activations. However, in practice, these activations are almost always matrices as well. And this comes from batching or sequence length in modern transformer networks or spatial dimensions in convolutional neural networks. So in practice, our neural network inference typically becomes just a sequence of matrix-matrix multiply calls. In a prune neural network, though, we're interested in the case when we've removed a bunch of the connections. And so we've zeroed out a bunch of the elements of A. So we end up with a sparse weight matrix A, getting multiplied by a dense weight activation matrix B, resulting in a dense activation matrix C. When optimizing any sparse matrix multiplication, one of the key challenges is optimizing for the memory hierarchy of the device. So here, for example, we have a fictitious memory hierarchy, but closely resembles modern CPUs, where we have DRAM all the way at the bottom, and the functional compute units or the fuse multiply add units all the way at the top. And so here, I'm just going to use lowercase letters to represent individual values of each matrix. And these all initially start all the way at the bottom at DRAM and must be moved all the way up to the compute unit where the fuse multiply adds that make up matrix multiplication can be performed. Ideally, though, we want to reuse values at higher levels of the hierarchy if possible, because this can greatly shorten the trip and speed up the computation. And in the best case scenario, all of the values are already in the register file. And actually on modern CPUs, some reuse at this level is required to fully realize the highest compute possible. And just to get a visualization of that, here we have a microarchitecture for a modern CPU. This is a fictitious one, but it closely resembles a lot of common CPUs. And so here we can see we have like 2 load ports that can move data from L1 cache into the register file. And we have 2 FMA ports that can perform 2 FMAs per cycle. So since we can only do 2 FMAs per cycle and 2 loads per cycle, this means that at least 2 of the operands for each FMA must already be in the register file in order to fully saturate those FMA units. The challenge here is that as we move up this hierarchy, these memory pools get smaller in size. And this is just usually a function of cost. The faster memory is more expensive, so they become progressively smaller in size. Luckily, as a community, we have a solution to this, which is tiling. Sorry, a solution to dealing with these smaller, progressively smaller sizes, which is tiling. So basically what we do is we take the large matrix multiplication problem in DRAM, and we'll instead grab a small subproblem to work at. And so, for example, here, this blue subproblem can now fit into cache, so this can be performed efficiently. And we can do this recursively to get even smaller problems that can now fit into the register file. So here we can see a small outer product. This is a typical approach on CPUs. And this would get placed completely in the register file and computed completely in the register file. Here at the bottom, we can see the code for that small outer product. However, performing register allocation, which is required, is challenging just looking at this code. So instead, most compilers will do what's called an unroll and jam, where they'll fully unroll this code to something that looks a little bit more like this. And this is the point at which register allocation can be performed fairly trivially. This is the key distinction between register tiling and cache tiling, is that this has to be done at compile time for register tiling, since the compiler is responsible for addressing the registers, whereas cache tiling, this can be done at runtime through the caching hardware. But why is this hard in the sparse case? So, for example, we have our sparse matrix A. This is the one we care about, our weight matrix. If we attempted to use a standard storage format, such as CSR, which would look something like this, where you basically compress all of the non-zeros in each of the individual rows, and then you store their original column indices as metadata. Then if we go to apply our tiling techniques again, we can do this fairly easily for the cache level. We can grab a small subproblem that could fit the cache. That's fairly straightforward. But when we go to grab our small register tile, we can now see that the non-zeros we've grabbed correspond to different locations in B through the indirection from that extra column metadata. And this makes register tiling at compile time tricky, because when we perform our unroll and jam, we can see that it's challenging to perform the register allocation because we have this indirection. So what ends up happening is that the compiler has to conservatively reload row 0 here, because it doesn't realize that within that A tile, both the first and the last value non-zeros are actually going to access the same row. It can't know this at compile time, so it has to be conservative and reload that row. And this means that those end up in separate registers. And so we don't get register reuse here, which is a problem for fully saturating the FMA units. And is also here, we can see that we've already also using more registers. So we've also increased the register pressure. So just an alternate way to kind of look at this to get an intuition for why this is challenging. We really want to make a 2D, we want to unroll along 2 dimensions. So we can get a 2D tile of C into the register file. This way we can have 2 operands in the register file and to fully saturate those FMA units. We can easily unroll along J because its iteration space is dense, because it belongs to both dense matrices. But unrolling along I becomes challenging because it has a sparse iteration space induced by this sparse matrix A. So instead of starting with a standard storage format like CSR, we kind of went back to the dense register tiling where we knew we would get great performance, or we get great register reuse, and said, okay, if our goal in the SpMM case is to skip specific operations associated with 0 values, so here, for example, if this middle element of the A tile is 0, then we ideally want to skip these middle 2 operations. And if the top element is 0, we want to skip the top 2 operations. If the bottom element is 0, then we want to skip the bottom 2, and so on. So as we can start to see, compared to our dense unrolled code, in the sparse case, there's actually many versions of this. There's many patterns here. And actually, the number of patterns grows exponentially with the height of this tile. And this can create an issue this can cause excessive branching, and also can cause increased instruction cache pressure if we were to actually generate all of these code for all of these cases. So instead of trying to generate code for all these cases, we want to try to figure out if there's a way we can generate less code overall. And so to get an intuition for that, we can look at 2 of these patterns. Here we have the blue pattern on the left and the red pattern on the right. And we can see that there's some commonality here. So they actually both compute the middle two operations, but the blue pattern then also in addition computes the bottom two operations, whereas the red tile skips this. But since this is sparse matrix multiplication, we can perform redundant computation. We can keep those zeros in. We can still perform the multiply by 0, and we won't affect the result. We will just be performing wasted work. We're going to be computing flops that are not actually required to get to the result. But if we're willing to make this trade-off, then we can actually just generate one piece of code that can execute both of these patterns. However, in the case of the red pattern, we'll perform redundant computation, and that's what we're representing here with this stripe pattern. And we call this merging of two patterns. But we saw how we could merge these blue and this red pattern, but then the question becomes about what about the rest of the patterns? Do we generate code for them, or do we also merge them? So to try to get intuition for like what are good merges and what are bad merges, we can look at these two on the right here. And here we can see that if we were to merge these two patterns, we would introduce redundant computation represented by the stripes in both cases. So this would probably be really bad. These would be bad candidates. Going back to our original two, the red and the blue, whether or not these are good candidates to merge kind of depends on how frequently we'll encounter each of these patterns. So for example, if we encountered the red pattern 100 times, or every one time we encounter the blue pattern, then we probably wouldn't want to merge these, because out of 101 iterations, we'll be performing redundant computation in 100 of them. So instead, we may want to generate specialized code for that very common red pattern, and instead merge that less common blue pattern with another pattern. That's what we can see here, where this blue pattern is now getting merged with this pattern on the far left. And we can actually kind of get an idea of what these frequencies are by just sampling our set of target matrices or using a random model. So then our problem now becomes, okay, we want to map all of the possible patterns to the set of patterns we actually want to generate code for. And so here, just to formalize that a little bit, we call the set of all possible patterns E, and the set of patterns we want to generate code for R, and we're trying to find a mapping from E to R. And here's an example solution to that problem. This is kind of a challenging problem. So to make it a little bit easier, instead of viewing mapping individual elements of E to elements of R, we instead view it as mapping subsets of E to elements of R. And this allows us to formulate it as a weighted set cover problem, a weighted set cover minimization problem, where G is our universe of all possible subsets of E, ideally the power set of E. We will prune this in some cases to make it more manageable, but in the ideal case, it would be the power set of E. And then we have our minimization function where we have a cost function for each subset. You can get more details about the cost function in the paper, but the main term I want to kind of point out here is this frequency term in the cost function. And this is where that frequency information is introduced to give the model an idea of how much redundant computation it's introducing by selecting any of these subsets to be merged together. So just to complete the formalization, we have our minimization problem. Then we also have the set covering constraint, which we need in order to ensure that all of the required patterns are covered by one of the sets. And then we also have a code size constraint. So this is where we can set a limit on how many patterns we'll generate in order to try to not exceed the code cache. So just to kind of cover what we've recap what we've covered so far. So we initially start by enumerating all the possible patterns that this tile of A could take. We then do some frequency profiling to get an idea of how common each pattern is. And then we feed this into our solver to solve for a mapping of E to R before we move on to code generation. So here for code generation, we have a tiled SpMM loop here where we just use an if statement to skip over the 0 elements. And then we can now take this outer product loop, that little register tile that we were looking at before, and we can replace it by our generated cases, our set R with a switch. However, there's still a challenge here because this switch is inside of this inner 4K loop. And this is not great because this means the code actually looks a little something like this, in which case on every iteration, we're branching to one of these patterns and the branch predictor can't really get a good idea of where it's going to go next and can't accurately predict this, causing stalls. So instead, we transform the code into something a little bit more like this, where basically we loop over all the iterations of the first pattern before moving on to all the iterations of the next pattern and so on. This means we take the code that looks a little something like this and transform it into something that looks like this. And in order to know which iterations belong to the first pattern, which iterations belong to the next, we have this pre-populated schedule that gets pre-populated by a scheduler program that also gets generated. This means that the final execution path looks a little something like this, where we actually feed the weight matrix first into scheduler code, which produces this schedule and maps all of the iterations of K to specific patterns. And that gets fed into the executor code, where our now dense matrix B gets fed in and gets multiplied against that sparse weight matrix A. So in something like an inference engine for deep neural networks, this would get split up into the model load time. So when you're loading the model into RAM, or whenever you're compiling the engine, you would run the scheduler code. And then during inferencing, when you're actually getting requests from the user, then only the executor code would run. So that's the key, that the executor code is very, very fast, but the scheduler code only really needs to be run once whenever you load up the model. And so just to kind of give a complete picture of how this looks, here we have that compile time flow that we discussed earlier, where we're doing the enumeration, the solving, the code generation, and then that generates code that then can go into something like this inference engine, this simple inference engine we have on the right. And we coined this this compilation flow unrolling sparse channel. So moving on to some quick results. Here we can see on the x-axis, we have loads per FMA. And this is just kind of a measure of how efficiently we're doing a register tile. It's basically measuring the amount of traffic between L1 cache and the register file. So the better the reuse, the less traffic between L1 cache and the register file. And we can see here that we have that one delineated, which is the one for our fictitious CPU, which actually is the same as like a Cascade Lake CPU. We would want less than one load per FMA to fully saturate those FMA units. And here we can see sparse register tiling does achieve that. So compared to our sparse competitors, we can see that we have better register tiling, like less loads per FMA, resulting in lower execution time. And compared to our dense competitor, here, the size of the bubble actually represents the amount of flops being performed. So we actually perform less compute overall, while having a slightly worse register tiling, but the lack of compute makes up. And so we ran our method on 2,396 matrices in the sparsity range of 60 to 95%, which is the common sparsity range for pruning neural networks, from the deep learning matrix collection with B column sizes of 32, 64, 256, and 512. And so here we can see, compared to our sparse competitors, across the board here for those sparsity ranges, we see higher throughput in required G-flops. Required G-flops is just the amount of flops that would be required to compute only with the non-zeros. And then compared to our dense competitor here, we can also see that we get better throughput across the board. We also implemented our method for ARM and integrated it into XNMPAC and ran it on a Raspberry Pi with a MobileNet V1. And we could see latency improvements there as well for the sparsity ranges of 70 to 90%. Here's just some interesting profiling results. So on the far left here, this is for a random matrix. We generated random matrices from 30 to 100% sparsity. And the plot on the far left is our execution time. So here we can see that blue, our sparse register tiling, has lower execution time in most cases. And in the middle graph shows how much redundant computation we are doing. So how much extra computation we're doing that wouldn't be required because it's computing with padded zeros. And in this case, we can see here that we do perform more redundant computation than our sparse competitors, such as MKL, SpMM, or adaptive sparse tiling, also known as ASPT, which only compute on the non-zeros. But looking at the graph on the far right, we can see that we have a better loads per FMA or a better register tiling, especially in this range of below 95%. And so our execution time is actually lower, even though we're performing more work. But we're performing less extra work than the dense case, which the redundant megaflops just increases linearly with sparsity. around 95%, we kind of just degenerate back down to almost basically what's a CSR, because we only have one non-zero per tile at that point. That becomes the most probable case. And so it effectively becomes a CSR style matrix multiply at that point. We can also see that sparse register tiling can compress better at lower sparsities, which can be important in some memory bound applications, like during the autoregressive portion of LLM generation, where you're only doing one token at a time, you're highly memory bound. So compression is very important in that case. And this is just because we actually only have one column index per tile, which can have multiple non-zeros, compared to something like a standard compressed sparse row or CSR storage format, where you'd actually have one column index per non-zero. Yeah, so that concludes my presentation today. I'm happy to take any questions.
Okay, looks like we have 2 questions.
Hi. So from what I understand, the motivation for doing this merging is the fact that the number of code patterns you need to generate scales exponentially with the size of your tile. But isn't the size of your tile implicitly bounded by architectural constraints? And from what I can guess, like the tiles, because they're bounded by the architecture itself, are going to be small. So I was wondering, like, whether this merging thing is useful at all, and whether you just tried the naive approach. Is that the size of the tile should be bounded, so it shouldn't really matter so much that it grows exponentially. It should just already be quite small.
Yeah, it's bounded to a degree. So if you're thinking of like an AVX512 architecture where you usually have like 32 vector registers, then you would want something. We would find that typically for like dense, we would want like a TI or like a height of that tile to be somewhere in the range of like 4 to 8, potentially even a little bit higher. And you'll see that the number of patterns can actually explode even with a height of 8, right? That's 256 patterns, right? That's a lot of cases to generate, and that's a lot of branching at runtime. So we definitely find that if we do generate all the code for every pattern, so that would be here, this case here, we do generate all 256 patterns, we actually do see a steep drop off in performance. You are right in the sense that like when we use a really short tile of 4, then we end up with the basic case of just generating every pattern. This is actually the best performance for those really short tiles. Specifically, like 4 is a common one that we use. When you have enough B columns that you can unroll in the other dimension enough to get a sufficiently large tile of C. So yes, in some cases, when you have lots of B columns and you're doing very, very large jump, a TI of 4 in generally every case is good. But for when you have slightly smaller B columns, then you'd want to move into something like a TI of 8. Sorry, TI is the height of the tile. And in that case, then you would want to do some merging for sure.
Hi, thank you for the talk. Following up on her question, I was wondering, how do you know the gains are from your exact method and not from any cache tiling methods you use? Like I see that you've used cake. How do you know that it wasn't the cake tiling? Because all the other methods you compared to are using some other dense tiling method or sparse tiling method. And then to her point, couldn't you, if you only have 256 cases for each matrix, even if you had 256 for each matrix in a neural network, can't you just auto-generate that before for inference, just grid search the right tile size?
Sorry, you may have to repeat the second part of your question, but I'll address the first part of your question first, which was, did we compare with basic register tiling? We didn't. I don't actually have those graphs here, but early on we did try just packing tiles in a standard CSR format using something like cake tiling, and this gave us some performance, but it definitely did not. It definitely didn't beat any of the competitors that we reported.
My question was like, if you were to change a cache tiling to something else, like would it affect the performance? Like if you remove
yes, absolutely. So I think there's kind of this situation where you have to have sufficiently good cache tiling in order for register tiling to matter. And so this is something where we didn't really look into something like sparse matrices, where cache tiling is like much less of a solved problem. Because with ML matrices is very uniform. So using something like dense tiling actually makes a lot of sense in this case, because the number of non-zeros per tile is like pretty uniform across all the tiles. But in something like sparse, where it could be like almost like a diagonal, like an identity matrix, right? Doing uniform tiling there doesn't make sense.
No,
And that's like having a good cache tiling is required to see the benefits from a good register tiling. But you can also have a great cache tiling. If you don't do the proper register tiling, you're not gonna reach peak performance, right? So they kind of go hand in hand. You really want to do both. You want to do both really well.
You want to do both, but it might not be as important, is what I'm saying, because many people have explored like the grid search method of getting the best register tile size, because there's not that many. So that's why I'm saying, like, if you were to ablate away the cache tiling, you might see some difference in performance improvement. That's all I was.
Yeah, for sure. Like if we didn't do an appropriate cache tiling, then register tiling wouldn't really matter. But you can also see, we also can see that if we just apply like cache tiling for something like a CSR storage format where there isn't sufficient register tiling, then we end up bottlenecked on that L1 to register, and we actually have a hard time beating dense in that case at the lower sparsities.
I think the outer product method is definitely better. And like, yeah, if you were to apply the cake to CSR, it wouldn't like work as well as you're saying. Yeah, that makes sense.
And sorry, the second part of your question was?
The second part was just about like her previous question, which was there aren't that many tiles anyway. So why can't you just grid search all of them before inference? Like, and then when you want to like run the model, put it on the device with the correct tile sizes for that network, that is.
Are you talking about the tile sizes or the patterns? Because yeah, for tile sizes, that's what we do. Like if we're picking between TI of 4, TI of 8 for a specific matrix multiplication, we just have like an empirical heuristic that we use to pick between those two options. We just generate both. But in terms of picking which patterns for any given tile size, that's where we use the minimization problem.
I see. Thank you.
I have a quick question about like your scheduling. Like, how expensive is your scheduling process compared to like usual gem packing registers?
Yeah, so it's pretty expensive-ish in the sense that like we didn't optimize this. There is ways to optimize it. There is ways to get better performance. Especially if you're starting from a dense matrix, it can be relatively cheap. But it's, when it comes to neural network inference, it's like not really that important because when you spin up a server, or if you're loading a model onto a device, the amount of inferences you are going to run and that time is going to definitely dominate over the scheduling. The scheduling is like not really perceivable to the user because it's under a few seconds, like for an entire model. So it's not like a huge penalty. And it's not something we really optimize. So it's not really something we really want to report timings on because it's not something we put effort into optimizing.
Okay, we have actually one more minute, so I'm going to selfishly ask a question, which is, so there's a lot of these types of methods that look at the sparsity pattern floating around for a bunch of different things. Do you see something emerging from it that is applied to a larger range of kernels in some sort of, like the way I can kind of do pragma unroll in a compiler now? Where do you see these types of methods becoming closer to something like that? Like if I was doing dense, that's how I would achieve register tiling. Do you see for like more general types of code, this type of optimization or pattern eventually percolating to that level of support?
Yeah, I think it would be really interesting to look at how this could be better integrated into an actual compiler flow. So something like Taco, where you know which dimensions are labeled sparse. Then if you did a pragma roll around that, then the compiler could do a technique like this and end up generating you a scheduler and the executor code automatically. I think that would definitely be a very interesting direction to see if there could be a better marriage there. It's just not something that we've like done a ton of research in, but I do agree. I think that would be a really cool direction. I think that would be, from a usability perspective, that'd be my dream. If you could just be like, this dimension is sparse and we want to unroll along it, we're going to apply something like this or something in this spirit.
Okay, thank you. Let's all thank the author for her talk. Okay. Sorry.